what you should know about energy and reactions. When you think of the term energy, you likely think of the buzz you get after you drink coffee or something like an explosion. In physics and chemistry, energy is described as the capacity of a system to do work. The two major forms of energy are kinetic energy, the energy of motion, and potential energy, which is energy that is stored. The chemical energy between bonds is a form of potential energy. When chemicals break and rearrange, some of the energy is released as heat energy. No matter what, the amount of energy in the total system always stays the same. The first law of thermodynamics makes this statement that energy can neither be created nor destroyed, so that all the energy in the universe always stays in balance, even while it may change to different forms. The second law of thermodynamics has to do with a concept called entropy. The Greek word trope means transformation. This word is used to describe the tendency of a system to be transformed into something with less order in it. When bonds between molecules are broken, things become more disordered. Some of the energy that was in that bond gets converted into heat, which can't be used to build new bonds directly. The second law of thermodynamics is that because entropy always increases in the universe, some energy is converted to unusable forms. Sometimes people say this energy is lost, but remember that the first law states that it's never actually gone, just not usable to build chemical bonds anymore. If you want to maintain order in a system, there has to be some sort of energy input to the system, like the energy you put in when you are trying to clean a room. Lucky for us here on planet Earth, the sun is a constant input energy, at least for the next 4.5 billion years. Maintaining life involves a lot of order, but thanks to sunlight and the ability of plant algae to convert the sun's energy into chemical bond energy through photosynthesis, life is able to happen. For any chemical reaction, the chemical or chemicals that we start with are called the reactants because they are the ones doing the reacting, and the chemical or chemicals we end up with are the products. Note that which chemicals we call reactants and which we call products in a chemical reaction depends on what reaction we are talking about. In this example, when we are thinking about a reaction that involves breaking a bond between these two things, we have one reactant and two products. However, if we talk about the reverse reaction, when the bond is formed, we now have two reactants and one product. Which set of chemicals you call the reactants or the products really all depends on how you write out the reaction and which way that arrow in the middle is pointing. When a bond breaks, it releases the energy of the bond. We therefore say that energy exits the system. The word for this type of reaction is exergonic. When a bond is formed, energy has to enter the system. This type of reaction is called endergonic. The term used for the energy contained in a system is the Gibbs free energy, named after Willard Gibbs, or G. For most equations calculating energy, we think of things in something called their standard state, which is a reference state of a chemical at a specific pressure. The Gibbs free energy of a substance at its standard state is a G with a little superscript circle. When we discuss the change in energy over the course of the reaction, we use the Greek letter delta next to the G because delta is the initial letter in the Greek word for difference. We can think about the energy in a reaction using a special kind of graph called a reaction coordinate. The energy, G, is plotted on the y-axis. The x-axis is a little weird because it doesn't actually have any units. Here we plot the reaction progress, which roughly corresponds to the time it takes for the reaction to happen, but it's never plotted with any measurable unit of time. Let's look at that exergonic reaction we talked about a few slides ago. Here, a bond is being broken, so we know that the products have less energy than the reactant. To show what happens to the energy during the reaction, a line is drawn connecting the reactants to the products. Note that I drew this with a little hump in it. That's because even for the most energetically favorable of reactions, a little energy input is necessary to get the reaction started, like how you need to light a match to start a fire or turn a key to start a car. This energy input is called the activation energy. The reactants at peak of this energy are in a special state called the transition state. For this reaction, this state is when the bonds are just about broken, but not quite. Think about when you stretch a rubber band until it breaks. The energy you put in when you pull on the rubber band would be the activation energy, and the point of maximum stretch just before it breaks would be the transition state. The delta G is the change of energy over the course of the reaction. When we work with an equation, we always subtract the initial energy, or the energy contained in the reactants, from the final energy, the energy contained in the products. Since in this reaction the products have less energy than the reactants, the delta G is negative. Any reaction with a negative delta G is said to be energetically favorable. An energetically favorable reaction with a large activation energy is going to happen slowly because of the energy needed to kickstart the reaction. A catalyst is a compound that helps speed up a reaction, often by reducing the activation energy needed to get things started. To do this, a catalyst might temporarily interact with one reactant to hold it in place, to make it more likely for the other reactant to collide with it. Or it might facilitate the transferring of electrons to form or break a bond. No matter how it works, the catalyst does nothing to change the energy of the reactants or the products, so it also never changes the delta G of the reaction. All it does is make it easier for the reaction to proceed. Most chemical reactions involve transferring electrons to break or form bonds. There are some exceptions to this: chemical reactions involving ions when two salts mix and recombine, or acid base reactions which involve a transfer of a proton. But all reactants in which electrons move about between reactants and products are called oxidation reduction reactions. Combustion reactions, such as the burning of methane, are one example of oxidation reduction reactions, often called redox reactions for short. The term oxidation was first coined to describe reactions using oxygen gas. It was later realized that when these reactions occurred, the oxygen atoms in the new bonds pulled the electrons away from the nucleus of the atom it reacted with, causing the other atom to lose electrons to it. The oxygen ends up with more electrons, therefore a reduced charge. That's where the name oxidation and reduction come from. But to help you remember which is which, the mnemonic oil rig helps a lot of people. For oxidation is loss, oil, reduction is gain, rig. Oxygen is one of the most electronegative elements, always hungry for electrons and pulling them away from other elements. You can have an oxidation reduction reaction with any strongly electronegative atom, not only oxygen, but oxygen is often the culprit. To think about some specifics of redox reactions, let's look at that methane combustion reaction again, but break it down to see where the electrons are in each bond. For methane, the electrons in each carbon hydrogen bond are tugged a bit more closely to the carbon. In each oxygen gas molecule, the electrons are shared equally, but when the oxygen reacts with the carbon and forms carbon dioxide, the oxygen tugs the electrons to its nucleus. In water, the oxygen is able to tug more electrons towards itself rather than to having to share within another equally electron greedy oxygen atom. So, in this overall reaction, carbon becomes oxidized. It forms more bonds with oxygen, which pulls the electrons away from the carbon. Each oxygen atom is reduced because when it is not competing for electrons with another oxygen, it gets to pull more negative electrons to its own nucleus. So, what's the deal with energy in redox reactions? Are they endergonic or exergonic? Well, they can be either, because transferring electrons sometimes involves forming stronger, more energetic bonds, and sometimes it involves forming weaker, less energetic bonds, or breaking bonds. Combustion is an exergonic reaction. It releases energy as heat and light. Photosynthesis is an example of a redox reaction that is endergonic, because it takes energy from the sun and uses it to form bonds. All that matters in redox reactions is that the electrons move around, and sometimes something is oxidized while something else is reduced. This whole time, when we've talked about reactions, we've thought of them going in one direction. In theory, all reactions are reversible, meaning that they can go forwards or backwards. In practicality, there are a number of reactions that reversing them is pretty much impossible. For example, if you burn a log, it's never going to reform that log again. These reactions are said to have gone to completion and are considered irreversible. Most reactions that happen in the cell are not nearly as extreme as burning something, though, so many reactions can be reversed. In these reactions, the rate of formation of products can eventually match the rate of formation of reactants. Notice those two arrows are now the same size. This is a state called equilibrium. When equilibrium is reached, depends on the delta G of the reaction and the concentration of all the components. In most reactions, one direction is somewhat preferred. So, usually your concentration of the reactants in the products isn't the same. See here that the amount of reactant is much greater than the amount of product, even though the forward and reverse reactions are going at the same rate. The thing here is that it's not changing over time. It's important to note that at equilibrium, the reactions haven't stopped happening, but they aren't changing anything in total. Thanks for watching.